Yeah, we had some issues with the training. We might want to train again. I think we already did it twice. If we could actually store the iterations of the training, that would be great. So I want to do it similar to the rhythm scan that is training on different datasets, different images. It's actually EEG turned into spectrograms, but then I like how the results are being presented. So we would like to do the same for the BreastMNIST dataset, for the malignant, non-malignant images of the breast. But if you can look at this image, this is another example that we have on the website. I would just like to do the training and everything in a similar fashion in terms of the output of the training. We want to display the accuracy and loss plot, the confusion matrix, and the misclassified images. Maybe not all of them in this case. In the rhythm scan, we only had 600 images, but now I'm pretty sure we have some way more. So the misclassified images would be just examples, just selected few. But yeah, we would like the training log with all the parameters as per the image attached.
To replicate the structure and presentation style of the results shown in the image for your BreastMNIST project, you can implement the following steps. When training the BreastMNIST model, store all training iterations, including accuracy, loss, and validation metrics, so they can be displayed for each run. This will allow you to track the model's progress across different epochs and compare results over multiple runs. Once the training is complete, generate plots for accuracy and loss across epochs, similar to the image. Use libraries like Matplotlib or Seaborn to create these visuals. For the confusion matrix, calculate the model's predictions on the test dataset and display the matrix as an image, ensuring clear differentiation between benign and malignant classifications. To address the misclassified images, select a small representative subset instead of displaying all misclassifications, particularly since BreastMNIST likely has many more images than your EEG example. Finally, the training log should include details such as test accuracy, training and validation accuracy and loss, model settings, and key parameters like batch size, learning rate, and optimizer. Storing these logs in a structured format, such as JSON, will allow you to dynamically generate the results page, enabling a seamless display of the plots, matrix, misclassifications, and logs. By integrating these features into the BreastMNIST visualizer, you can replicate and enhance the level of detail and interactivity seen in Rhythm Scan.
Yeah, this will get quite complex. So we also have obviously we have all the code for Rhythm Scan, and we'll actually want to see if we can essentially do the same. So I might share the code with you, or should I share the structure for the project? Yeah, it has a lot of PNG images. Well, Rhythm Scan has actual images, but the BreastMNIST it doesn't have the raw images. It has a folder, a file, compressed file with all the data in it. So that will be the main difference. But yeah, but if you can have the code for Rhythm Scan as reference, that will be great. But I'll just share the Rhythm Scan project structure with you.
Looking at the structure of the Rhythm Scan project, the main difference between it and the BreastMNIST project lies in how the data is stored and accessed. Rhythm Scan uses uncompressed folders with categorized image datasets, while BreastMNIST relies on a compressed.npz file to store the data. To adapt the Rhythm Scan code as a reference for BreastMNIST, you would need to add a pre-processing step to handle the compressed dataset format, extracting and organizing it into a structure similar to Rhythm Scan before training or visualization. The static folder in Rhythm Scan contains results folders for each training run, storing logs and outputs like training plots. To replicate this functionality, the BreastMNIST project should implement a similar mechanism, automatically generating and saving results after each training iteration. This will allow dynamic visualization of metrics such as accuracy and loss, confusion matrices, and sample misclassifications. The training scripts, such as trainbetter.py, can serve as templates. Modify them to accommodate BreastMNIST specific parameters, such as its image size and binary classification tasks. The front end in the template's index.html file will also need adjustment to reflect BreastMNIST specific terminology, such as benign and malignant instead of seizure and non-seizure. The app.py file provides the backbone for the RhythmScan project. Use it as a reference to set up a similar Flask application for BreastMNIST, ensuring that the workflow for training, saving results, and displaying visualizations remains consistent.
Okay, so couple of things. So first of all, we want to move away from Flask. So yes, we're doing all the training in the backend, which should be okay, but happy for you to comment on that. Then we each iteration of the training, we would like to store the results and display performance like we do with RhythmScan, like in the image I shared with you earlier. So we would like to replicate that. The loading of the file, loading of the data can be custom for the BreastMNIST data file. I think it's a compressed data file, but yeah, I don't care how you process it. So the most efficient way you can choose which way you prefer. So to sum up, we don't need Flask in this case, but essentially don't run anything in the backend. I think eventually, once we deploy the web model, can the web model, considering its Keras JS, minimized version of Keras, that should be able to run in JavaScript. Is that correct?
Moving away from Flask for this project is a good choice if you want the entire workflow to run on the client side without relying on a back-end server. This approach simplifies deployment and ensures the application is self-contained, especially since TensorFlow.js supports running machine learning models directly in the browser. By converting your Keras model to TensorFlow.js, the training and inference processes can be implemented entirely in JavaScript, eliminating the need for Flask or back-end computation. For each iteration of training, you can store results such as accuracy, loss, and validation metrics directly in browser memory using JavaScript objects or local storage. These results can then be dynamically displayed on the page, replicating the performance visualizations seen in RhythmScan. For the accuracy and loss plots, you can use libraries like Chart.js or D3.js to generate and update them in real time as the training progresses. The confusion matrix and misclassified image display can be implemented similarly by updating the visualizations dynamically based on the training output. Loading data from the compressed BreastMNIST.npz file can be handled by pre-processing it beforehand into a more convenient format, such as a directory of images. Alternatively, you can load and parse the .npz file directly in JavaScript using TensorFlow.js's tf.data API, which supports custom data loading pipelines. The choice depends on whether you want to keep the pre-processing step external or integrate it fully into the web application. Using TensorFlow.js to deploy the model is indeed a feasible solution. Once the model is converted to TensorFlow.js format, it becomes a lightweight, browser-compatible version of the original Keras model. This version runs efficiently in JavaScript and can leverage hardware acceleration via WebGL. By taking this approach, you ensure that the tool remains scalable, responsive, and accessible to users without requiring back-end infrastructure.